Good morning all. Today we will discuss 8085 microprocessor instruction set. So 8085 microprocessor IC, whenever you can use in a microprocessor system. So for the programming purpose, there are total 74 number of opcodes, that is the operational codes, and total 246 number of instructions. So to understand the instruction set, the complete instructions of 8085 microprocessor has been categorized in 5 segments. So that is shown over here. The number 1 is data transfer group, arithmetic group, logical group, branching group, and the machine control group. So every group contains some set of instructions. So one by one we can go through each segment and discuss the function of these instructions. Then we will go for some examples. Fine. So first is the data transfer group. The instructions belong to data transfer group that can be used to transfer the data between two registers, register to memory, memory to registers. And all instructions under this group have no effect on the flag registers. So we can go to the data transfer group instructions elaborately. So here the data transfer group instruction format. So before going to the instruction format, we can explain basic format of instructions, and we can go through some examples of the instructions like MVI small r, the data 8-bit. This is the basic format of the instructions, where MVI is the opcode or the operational code that is to be happen, and R over here is the operand, data over here is the operand. So here small r can be defined by some registers like accumulator P, C, D, E, H, L, or the M, the memory and data. So examples, the mnemonics is like MVI A32. So what is the function of the MVI instruction? The MVI instruction can be used to store any 8-bit data into the registers, which is defined into that position. So this is the basic format of the instructions, which is defined in this part. And we can define each instructions by a method called the arrow notation. So first of all, I am going to define or explain what is actually the arrow notation is called. Say if we write down the A, means is define the accumulator only. If we write down the A within a first bracket is called the data which is stored into the accumulator. Similarly, if we define a B only, so it define the register B itself, and which we define the B within a first bracket, it define the data which is stored into the register B. And with the arrow, direction of the arrow, we can show the flow of the data from one entity to another entity, like one register to another register. Example, say if we define the arrow in this way, so content of the B register will move to the accumulator. So define in this way, we can define the annotation of each instruction individually. And side by side, we are going to discuss the addressing mode also, that the instructions belongs to which addressing mode, that also we can define in this part, and the word size also. That means how much byte instruction is this, how much byte is used to load these instructions in the memory of 80 microprocessor system. Fine. So here the examples are like the MVI A32. So where MVI A32 is the data, the 8-bit data, which will be stored into the accumulator. Similarly, if we say that MVI, then space M, there's 4VH, that means the 4V is the data which will be stored into the memory. So using the annotation, how we can define that? So before going to the annotation, one thing I am going to tell you, that this mnemonics, that is MVI 32, whenever this instruction is going to be loaded in the memory locations of the memory which is attached to the microprocessor system. So here it is 2-byte instructions. Why it is 2-byte instructions? Because whenever we can see these instructions clearly, that we have to find out whether there is a data or address. So in these instructions, we can see that 32 is the data itself. So it is a 1-byte data, and the rest of the part in the A. So for the in the A, one hexadecimal code is assigned already, and the chart which is predefined or is given to you all, so we can find out the allotted hexadecimal code for these MVI instructions. So this is the hexadecimal code that is for the 1 byte, and 32 itself is another 1 byte. So complete instructions belongs to 2 bytes. That means 2 bytes are required to represent the instructions. That is what is called the 2 byte instructions. So here is the 2 byte instructions, right? So whenever these mnemonics can be converted into the hexadecimal code and it is loaded into the memory location, say for example 8000. So I am going to the 8000 memory locations and load the hexadecimal code for MVI. So MVI has been loaded into the hexadecimal code into 8000 memory locations. So now we are going to the next memory location like 8001. Then here we can load 32, the data itself, right? So whenever microprocessor going to the 8000 and take the hexadecimal code, decode it, I can understood, okay, here is the instructions where some 8-bit data can be loaded into the accumulator. So which data should be loaded to the accumulator? So to find the particular data, microprocessor has to go in the next memory location, that is 8001. So 32 can be found and loaded into the accumulator, right? So this is actually the functions and working flow, how the microprocessor can execute a particular instructions. So in this way, we can explain that how to write the annotation. See, here 32 is the data which should be stored into the accumulator. So here write down the accumulator within a bracket and give the arrow in the directions and write the second byte. Why the second byte? Because MVI that represented by an hexadecimal code, and that is the first byte. Okay, so that is the first byte. And what is the second byte? The data itself, 32. So this second byte data should be loaded into the accumulator. Correct. So this is the annotation for MVI. Similarly, we can explain for the MVI M4B also. So what is the M? M represents as memory locations. Which memory location? The locations which is loaded into the H register. Simple like that. Say in the memory. In the memory, say there is 8000 memory locations. So it is like a registers where you can store a particular data in the memory which is connected to the 802 microprocessor system. And we can define this 8000 by a letter M. And if we give some data to the M, so directly the data will be stored into this particular memory locations. So the question is how to define the M and how to give the data into the M. Very simple. In the architecture of 802 microprocessor system, it is predefined that M directly related with the H and L. So if we are going to identify the 8000 memory location by the M, it means the 8000 should be stored into the H register pair. Very simple. So we can store the 80 in H register and 00 in the L register. Very simple. So M directly defined as 8000. If I am going to store some data in 8001, so we have to define the 8001 by M. And how we can define that? We can store the 8001 in H register pair. So simple, we can store 80 in H register and H register we can define the 80 and in L register we can store the 01. So automatically M is equal to 8001. Right? So this is the register indirect addressing mode. It belongs to the register indirect addressing mode because we are actually accessing the address but not directly, because the address will be not written in the instruction directly. The address will be defined by some register like entity called the M. Okay, and that is dependent on the value of H register pair. So that is why we can define as a register indirect addressing mode. So here the 4B data will be stored into memory, but memory also defines some memory locations for the address. How? The content of H, content of L that define the value of the M. That define the value of the M. Okay, like M is a pointer, then we give like a pointer like that. So that is how we can define H within a bracket, L within a bracket, and whole bracket. Say if you are going to store 4B in 8001, so store the 80 in H and 01 in L. So only H define the H register itself, H within a bracket define the 80, L within a bracket define the 01, and whole bracket define the 8001 within a bracket. That is the content of 8001. So whenever we write the second byte itself over here, it means the second byte data will be stored into the 8001 memory locations. Okay. So that is the actually procedure of how we can explain the function of each instructions by the annotations. Fine. So it is the immediate addressing mode actually. because immediately we can store the data into the memory in that case. So it is the MBI. Actually, addressing mode defines that how we can find a particular data. Say we are going to store a particular data into the accumulator. So we can find the data from the registers, we can find the data from the memory locations directly, and the register can be written directly in this particular instructions. We can find the data from the memory locations, but the memory location can be pointed by some external pointer like M, and we can find out the data through the M. So depending upon that case, we can define as addressing mode. There are basically 5 addressing modes in the microprocessor system: direct addressing mode, register addressing mode, indirect addressing mode, register indirect addressing mode, implicit addressing mode, in this way. So actually this belongs to immediate addressing mode, because here the data itself which are going to store somewhere else, the data itself is stored into this particular instructions. Okay, so remember that where the data will be stored doesn't matter with the immediate addressing mode. Actually, from where we can get the data actually. If the data itself will be stored into this particular instructions, that belongs to the immediate addressing mode always. But whenever we are getting the data from the M, example I can give you some. That instructions we will discuss later, but I can explain to discuss the register indirect addressing mode, like move AM. So here the content from the M will transfer to the accumulator, but that means we can store the data into the accumulator. It is a register, but from where we can get the data? From our memory locations, but that locations is not defined in the instructions. That memory locations can be pointed by some pointer like M. So through the M pointer, indirectly we can access our memory locations to get the data which will be stored into the accumulator. That is why these instructions belongs to the register indirect addressing mode. I think it is very clear to you, but this belongs to the immediate addressing mode, because where the data itself will be written in the instructions, which will be transferred over in the another registers or memory locations. This belongs to the immediate addressing mode. So it is immediate addressing mode, and definitely it is a 2-byte instructions. Next, another instructions is MOV. So the opcode, operational code is MOV, and R1 and R2 is the operand. So better I can erase. Next, so MOV is another opcode. R1 is operand, R2 is the operand 2. So here the first operand defines the destination, and the next is the source registers. So what is the function of the move instructions? Very simple. Here the content of the registers which is defined in the next position is the source registers. The content from these registers will move to the destination registers. This is the copy paste, not cut paste. So R1 and R2 defines the accumulator B, C, D, H, L and M. So examples like move AB. So very simple, the content of B will transfer to the accumulator, and as we know, the register set for 80 microprocessor system that there are accumulator, flag, B, C, D, E, H and L. These are the 8-bit registers normally, and there are 2 actually 6-bit registers, that is stack pointer and the program counter. So the accumulator, the B register, the C or D, whatever it is, can contain maximum of 8-bit data or 1-bit data. So move AB means the content of B register will move to the accumulator. Very simple. So we can define by the annotation. We can write down the B within a bracket, that means content of B. Here accumulator within a bracket, that means an arrow is in the direction. So content of B will move to the accumulator. Simple. So it defines the register addressing mode. Now move DM. So here the M is register like entity. It is a pointer which point a particular memory location. Which memory location? That is stored into the H register pair currently. So this content from this particular memory location which is pointed by the M will be transferred to the D register, and the memory which can be used to interface with the 80 microprocessor system, in the memory, in each box of the memory, in each location of the memory, maximum 8-bit data can also be stored. Very simple. So that is why this data can be transferred to the D registers. Okay. So how to define the M? M is defined by the content of H, content of L and whole content. So that content which is stored into this particular memory location, which location, that is defined by the H register pair. So that will be transferred to the D registers. And last is the move MC. So here C will be transferred to the M. Okay. So what is the addressing mode? Move AB. It is the register addressing mode because we can find the data from the registers like a B. So Okay, so this is a register addressing mode, and move DM. So here we can find out the content from our memory locations, but that locations can be defined by the M. So definitely defines the register indirect addressing mode. Okay, and the last one is we can find the data from the C. So it belongs to it is also belongs to the register indirect addressing mode, and 1 byte instructions. It is also 1 byte instruction, and it is also another 1 byte instructions. So we can go to the next slide then. Okay, fine. Okay, so here is a program. So as a beginner of microprocessor programming, we can explain this program like swapping the content of register B and C. So how to write a simple program? So first we can take an example like C. We can take a register like B. We can take a register like C. Okay, and using the program we can store some 8-bit data into the B and as well as the C. So for example, as an example that we can take over here, we can store the data 31H. It is in hexadecimal format. As you know, the microprocessor always use the data system as hexadecimal number system. Okay, and the programming language in assembly language programming. There are some other language programming like machine level language programming or high level language programming, but microprocessor system 8085 use the assembly language programming, and the data system can be used over here is number system is used as hexadecimal number system. And in the C register another data like 32 can be stored over here. So what you have to do? We have to first store a 32 data into the B register, store 32 data into the C registers, and we have to swap between two registers. So how we can do that? Very simple. Then we can take another registers like accumulator, and we can move the content of B from B to accumulator. So it is 31. Next we can move the 32 from C to B. So automatically 31 will be replaced by 32, and then content of accumulator will move to the C registers. So 32 will be replaced by the data 31. So automatically the data will be replaced between each other. So it is a very simple to understand the algorithm, and depending upon this process we can explain one by one the instructions. So first what we can do, we can simply store the 31 into the B registers. So here we can write down it is a MPI B and 31. So 31 data will be stored into the B registers. Then MPI C 32. So 32 will be stored into the C registers. Then we can store the content of B to the accumulator. So move AB. Here B is the source and A is the destination. So content of B will move to the accumulator. Then simple move BC. So as we have discussed, the content of C will move to the B registers. So content of C will move to the B registers over here. Then move CA. So accumulator content will move to the C registers. So we can write down over here. Then we can write down the halt instructions. So halt instruction is always required to stop this the execution of the program. And whenever this mnemonics, which is written in this assembly language programming, can be converted into the hexadecimal code, because in the microprocessor system there are the options to load only the hexadecimal number systems from 0 to 9 and A to F. So every instructions opcode actually is converted into some hexadecimal code, and every hexadecimal code is 8 bit or 1 byte. So one chart is given, and depending from this chart we can take the hexadecimal code of every instructions and convert it into the hex code pattern. See over here, and every machine, every microprocessor system has some starting address. Why it is starting address? Because we know the 8085 microprocessor system support 8-bit data, because it is a 8-bit processor. It is a 8-bit processor means maximum 8-bit data can be accessed by the microprocessor at a time, and data bus is available is only 8-bit, but the address bus is available is 16-bit. Okay, so maximum 60-bit address can be accessed by the microprocessor. So everything is, if it is defined in hexadecimal number system, so address must be from 0000 and end in FFFF, and definitely it will depend. It depends on the interfacing of the microprocessor system with some EPROM or EPRAM structures. but these are different things that we can discuss in some other slide. But here I am going to explain the starting address of the microprocessor is 0000H. But why we are not going to take this memory locations to store our programmings? Because every microprocessor system has some particular operating system, some predefined program which is already loaded by the manufacturer of the microprocessor kit. So this program always will be loaded starting from 0000 memory locations, and say some memory locations are required to load this particular predefined instructions like operating system of any system of any machine. So see, if it requires say 7FFF, say from 0000 to 7FFF, these locations belongs to the ROM locations, the read-only memory. So after that 7FFF, the next memory location is 8000. So from 8000 to FFF, these locations are available for RAM, random access memory, which can be used as cache memory where you can store some programming. Okay, so that is why every microprocessor system has a particular starting address, but it is not mandatory that every system should have a same starting address, depending upon the capacity of the operating system. So depending upon the capacity of operating system, we can know what is the starting address of the particular microprocessor system. So for an example, we can take over here that we have a microprocessor system where the starting address is 8000. That is why 8000 is written over here, not 0000 memory location. So okay. So how to convert into the programming into the hexadecimal code? It is also very simple. First, go to each instructions individually, and we have to find out whether there is a data or address in the particular instructions. If there is a data or address with that particular part, for the rest of the part, one opcode has been assigned, and we have to find out the opcode from the chart. Very simple. So first is MPI B31. So here, what is the data? Data is only the 31 is the data. So leave that particular part. So for the rest of the part, for the MPI B, there should be a particular hexadecimal code what is predefined in this chart. So from the chart, we can find out the particular hexadecimal code, and the code is 06. So we can write down 8000 and 06. It is the hex code for MPI B. Then that is already loaded into the particular memory location 8000. So rest part is 31. So definitely in the next memory location we can store the 31. Very simple. Second byte. So two memory locations are required to load this MPI B instructions completely, including the MPI B opcode as well as the data itself. So this complete instruction has been loaded in two memory locations. That is why it is called the 2-byte instructions, because 2 bytes are required. 06, the hex code for the MBIB itself, it is a 1 byte, and 31, the data itself, it is a second byte. So 2 bytes are required to represent the particular instruction. That is why it is called the 2-byte instruction set. Okay. Similarly, MBIC also. So MBIC has a particular hex code like 0E. So in 8002, 0E has been loaded. 32 loaded in the next memory locations. But move AB, in these instructions there are no data, no address. That means for move AB completely, one hexadecimal code has been assigned. So that is 78. So in 8004, 78 has been stored. Similarly for move BC also 41 has been stored. Move CA 4F stored, and all instructions 76 has been stored. So in the form of hexadecimal code, we can go to the microprocessor system, we can enter the code one by one, and we can execute the program, and we can check the results. Okay. So it is a very simple thing that how we can write a program in mnemonic format, how we can convert it in the hexadecimal code. So that's all. And okay, so it is written over here also. Here starting address of the RAM has been considered as 8000, but it is not necessary that every time we can consider as 8000, because it's dependent on the manufacturer of the kit. It depends. Okay, it will vary. So next we can go to the next slide. Okay, so that is already discussed. Program 2, I think not required. Next instructions. Okay, fine. So another instructions that also belongs to the first data transfer group, LXI. Then RP defines a register pair and the 16-bit data itself. What is the register pair? We know that 8085 microprocessor system, this IC has some particular memory called the registers, but little bit number of memory. So we can name as a registers. Okay, like a register A called the accumulator, the flag register is a special purpose registers, the B, C, D, E, H and L. So every register can be used as a simple data transfer register. We can load the data other than the flag registers directly. We can store the data into the accumulator B, C, D, E or H or L. And sometimes whenever it is required, microprocessor can access the 16-bit data, but not at a time, one by one, but we can load the 16-bit data into the microprocessor system using the programming, using the assembly language programming, where we can consider two 8-bit registers as a register pair. See, here B is a 8-bit registers, C is 8-bit registers individually, but whenever you consider B and C both simultaneously, it defines as register B. And whenever we are taking the register B in a programming purpose, we can load a 16-bit data into the register B very easily. Similarly, the D and E also can be considered simultaneously to define the register D as well as the H and L also. But it not mandatory, it not like that B and E can be combined as a register. It's not like that because the architecture is predefined. Okay, so B and C can be used as a register pair. Using some instructions, we can use this register pair to store the 16-bit data. But it is very important to understand that microprocessor always access the 8-bit data at a time. So if any 16-bit data or address is given to the microprocessor, not address actually the data, then microprocessor access the lower byte first, then higher byte. Okay. Say if any data like 8050 has been given to the microprocessor. So here 80 is the higher byte, 50 is the lower byte. So if we have a register pair like HL register pair, H register pair, and 80 will be stored into the H register and 50 will be stored into the L registers. So first microprocessor will take the lower byte first and store into the L registers, lower byte registers, then take the higher byte, then store into the higher byte registers. Okay. So next go to this instructions format like LXI, register pair, data 16-bit. Here register pair defines the register pair like B register pair, D register pair, A register pair, and the stack pointer also. What is stack pointer? Stack pointer is a predefined 16-bit register which can store the address of the top of the stack. Okay, so it is a 16-bit registers of the microprocessor system. And we have another 16-bit register also, that is on the program counter. Program counter always holds the address of the next instruction to be executed. Actually, the program counter always control the flow of the execution of the microprocessor system. Microprocessor always execute in a forward pattern, like starting from 8000. Say for example, then 8001, 8002, 8003 in this way. And how it can happen? Whenever microprocessor is accessing 8000, automatically program counter holds the next instruction, next address 8001 by default. And after the complete execution of 8000, microprocessor will check what is the content of program counter. Okay, it's find 8001. Okay, then go to the 8001. And whenever microprocessor go to the 8001 for execution, automatically program counter increment itself to 8002. It is an automatic process. So after the complete execution of 8001, then microprocessor can go to is going to check what is the content of program counter. It's found 8002. So microprocessor go to the 8002 and program counter increment itself. So on. So if we are going to break this common execution process, they're very simple. We are going to change the value of the program counter. Say now 8001 is accessing. For example, microprocessor is going to execute the 8002. So automatically what happened in the program counter, the value is automatically 8003. But now I am going to check that after the execution of 8002, microprocessor should go to 9002. So by default or forcefully by instructions, if we change the value of the program counter to 9002, then what will happen? Microprocessor after the execution of 8002, it can come back to the program counter for checking what is the content which is stored in the program counter. It found 9002. Then fine, okay, then go to the 9002. Okay, don't go to 8003. It jumped to 9002. So in this process, we can use the call instruction, jump instruction. That also will be discussed later. So these are basic function of the program counter. So there are some two 16-bit registers, stack pointer and program counter. But now I'm coming to our main lecture, that is LXI. So what is the function of LXI? Very simple. That 16-bit data which is stored, which will be stored into the register pair, B register pair, D register pair, or H register pair, or stack pointer. Very simple. Next example is LXI H9005. So here 9005 is a 16-bit data. So here is 16-bit data. So for LXI there is one hexadecimal code for opcode for LXI which is defined, and 90 is another 8-bit or 1 byte data. 05 is another 8-bit or 1 byte data, means lower byte. So 3 bytes are required to represent the instructions completely. That is why it is called 3-byte instructions. And the data itself is loaded into this particular instruction. That means it is called immediate addressing mode. It belongs to the immediate addressing mode instruction, addressing mode set. Okay, so it is immediate addressing mode and it is a 3-byte instructions. So in this way we can find out that these instructions belong to which addressing mode. We can find out very easily, and how much byte instruction is this. So here in A register, which will be loaded, 05 will be loaded into the A registers and 90 will be loaded into the 8 registers. But as I have told you that microprocessor always access the lower byte first, then higher byte. So first in 8000 memory location, I am going to enter the opcode for LXI-H, say 21. 21 is the hex code for LXI-H. Entering the 21 over here. Then in 8001, which I am going to enter, I am going to enter 05. Why? Because in the next time which we have to enter, that will be stored in the A registers. That is why lower byte first should be entered. Then in 8002, then 90 will be entered, which will be stored into the 8 registers. Because microprocessor always will access the lower byte first, then higher byte. That is why 05 will be entered second. That is why 05 can be called as a second byte, and 90 will be called as a third byte. Okay. So now come to the annotations. So which will be loaded to the L? The second byte. Second time which will be entered, that will be loaded into the L. That is why in the annotation we have written L arrow towards the L, second byte over here. And third byte means third time which will be loaded. That is the 90, that will be stored into the H registers. So that will be stored into the H. Correct? So it is the procedure to represent the function of any instructions by the annotations. Similarly, I am going to erase this. No, this. Okay. Fine. Next is LXI stack pointer. This, so stack pointer can be defined as a FFFF. We know that stack pointer is a stack. Stack is a part of a memory. Some consecutive memory location can be defined as a stack, and that will follow a particular algorithm called the LIFO algorithm, last in first out. So here all the data will be entered in one directions and will be stored one by one and top of the stack. So wherever we are going to retrieve the data, means pop the data from the stack, so the top of the most data will be retrieved first. So this algorithm is called the last in first out algorithm. So what to do? How to define the stack in the microprocessor system? The first memory location should be defined maximum value like FFFF, and the stack in the microprocessor system will be in the decreasing order. So if we are going to load our next data into the stack, so definitely the next data will be stored into FFFE location and so on. So this stack is in the decreasing order. So the stack will be in the decreasing order. Correct. So here LXI is stack pointer, then we can define the address. In this we can define the address of the stack pointer. Here stack pointer can be defined as stack pointer lower byte and stack pointer higher byte, 8 and 8 So second byte will be stored into the stack pointer lower byte, and another third byte will be stored into the stack pointer higher byte. Okay, fine. So it is written over here for 16-bit execution. Microprocessor accesses lower byte first and then higher byte. Next instruction is LDA. LD is another opcode, operational code, and address is the operand. So here after LDA we can directly write down the address. This is the direct addressing mode, because here we can directly take the data from the address, which will be defined in this position and stored into the accumulator by default. In the microprocessor system, accumulator is a default register, and flag registers also are default registers where we can store the status of the any arithmetic operations or logical operations. Okay, so after any arithmetic or logical operations, what are the changes happening from in the result, that will reflect in the flag registers like carry bit, parity bit, auxiliary carry, 0 bit, sign bit. Everything belongs to the flag register. It is also 8-bit data, and every bit has a particular significance. There are 5 number of flags. So after any arithmetic operations, if carry has occurred, so carry bit will be 1, otherwise not. If auxiliary carry has occurred, so auxiliary carry will be occurred or not 1, otherwise it is a 0. In this way. So accumulator is a by default register. So every time after doing any arithmetic operations or any data transfer, if any register is not defined by default, accumulator can be taken as a default registers. So here LDA is a opcode. Okay. So here the default register is always the accumulator. Here address is defined. So this address contains a data which is a 8-bit data. So that 8-bit data will transfer to the accumulator. So this address belongs to the RAM or ROM, whatever it is. The content which is stored in the particular memory location will transfer to the accumulator, which belongs to the microprocessor IC, 8085 IC. Okay, so example LDA 9050. So in microprocessor RAM is a box, and there is a small box called the memory locations like that. So here, say this is the box which has the memory location 9050, and this box contains the data 32, for example. So if we write down LDA 9050, so what will happen? The content which is loaded into 9050, that is 32, will transfer to the accumulator, and accumulator belongs to the microprocessor IC. So here 90 is the higher byte, is third byte, 50 is the lower byte. So here we write down the accumulator annotation. Third byte means third time which is enter, 90. Second byte means second time which is enter, so 50. So here annotation is like that: third byte within bracket, second byte within bracket, whole bracket. Whole bracket means because whole bracket of 9050. So the content which is stored into the 9050 memory location will transfer to the accumulator. Okay. So this instruction belongs to direct addressing mode and is a 3-byte instructions. Because 3 bytes are required to represent the complete instruction, that is why it is a 3-byte instruction set. And directly the address from where you can get the data, this address is stored is written in the instructions. That is why it is called the direct addressing mode. Very simple. So next. Okay, fine. So I think okay. Okay. So another instruction is STA. STA is just opposite of LDA instructions. In the LDA instruction, whatever we have discussed in the previous slide, that the content of this memory location, which is defined after the LDA, will move to the accumulator. Here STA is just opposite direction. Means the content of the accumulator will move to this particular memory locations, which will be defined in the instructions, right? So STA then address. So these instructions store the content of accumulator in the memory address defined in the instructions. Okay. Example STA 9080. So in 8080 microprocessor system, say in the accumulator the data is 32, for example, and in the RAM or ROM there is a memory locations. Say it is a 9080 memory locations. So content of accumulator, that 32 will copy to this particular memory locations, right? 32. So ST means the content of accumulator will move to this particular memory location which is defined over here. Annotation is same as the LD instructions, just direction is opposite, because here the content of accumulator will move to accumulator to another memory locations. So these are the function of these instructions. Next instructions that also belong to the this data transfer group instructions, that is LHLD address. LHLD address means the address which is defined over here. The content of this address will move to the L register by default, and the content of the next memory location will transfer to the H register by default. Okay, LHLD instructions directly related with the H and L only. In this context, I am going to say another thing. Whenever we are going to discuss about the default registers of 8-bit, it is accumulator. By default, it is a default registers of microprocessor system for 8-bit applications. And whenever we are going to do any 16-bit applications, so always the default register is H and L. H register there. Okay. So here, example. Right now I am going to example, that is LHLD 9080. So the content which is stored in 9080 memory location will transfer to the L register, and the content of the next memory locations, that is 9081, will transfer to the H registers. Okay. So definitely it is 3-byte instructions, and 90 is the third byte, 80 is the second byte. So in annotation is written third byte, second byte, whole bracket, transfer to L registers. third byte, second byte plus 1. It means the next memory location's content will transfer to the H registers. So using LHL instructions, we can transfer two consecutive memory locations into L and H. Similarly for the SHLD instructions also. So using SHLD instruction, we can transfer the opposite. So content of the L and H will transfer to the particular memory locations. So example, SHLD 9080. So content of the L will move to the third byte, second byte, and content of the H will move to the third byte, second byte plus 1. That means the next memory locations. So next is another is LDAX RP. Here LDAX is the opcode and RP defines the register pair. So it defines the B register pair and D register pair. Here for the instructions only two register pairs can be used over here. Only B and D. H register pair cannot be used in these instructions. Okay. I am going to directly go into the examples because it is like a register indirect mode instructions. In this case also, what to do? Example LDAXB. So content of B and content of C defines a particular memory locations. That content of that location will transfer to the accumulator. Okay. So similarly for the STX also just opposite. So content of the accumulator will transfer to the D and E registers XT. So LDX is the memory location content which is defined by the one register pair transfer to the accumulator. STX just opposite. And last instruction is exchange XCHG, where by default it will occur it will just exchange the data between H register pair and D register pair. Okay, so that's all about the instruction set of the data transfer group only. Thank you.